instrument transformers and advanced sensors, voltage transformers and resistive dividers. All right, let's dive right into this. Welcome back to The Explainer. Today, we're setting the stage to completely finish off your mastery of the marine switchboard sensor ecosystem. In our last breakdown, we looked at how to safely monitor massive amounts of current. But, a power plant isn't just about current, it's about voltage too. And when we're dealing with marine medium voltage switchboards, we're dealing with some serious, absolutely lethal power.
So, this brings us to a really massive, high-stakes safety and engineering problem. Think about it for a second. How do you safely measure 6.6 kilovolts? You absolutely cannot just slap a standard multimeter directly across a live marine busbar. The sheer energy would literally vaporize the equipment and potentially the technician holding it, which is obviously a no-go. We need a way to step that massive voltage down to a safe, readable level without losing the accuracy of the measurement, all while keeping a solid physical barrier between that deadly primary voltage and our sensitive protection relays.
Just to quickly set our bearings based on where we left off, we've already locked down the current side of the equation. We saw how current transformers and Rogowski coils act as the eyes of the protection relays by scaling down massive amps into tiny, easily measurable signals. With that covered, our focus shifts entirely to the other half of the power equation. Let's tackle voltage and look at the actual hardware designed to safely capture it.
Well, the traditional solution to this voltage problem is the conventional voltage transformer, or VT. On marine medium voltage switchboards, these guys are heavily resin insulated, and when it comes to how they're physically mounted inside the cabinet, you'll generally encounter two styles. First, they can just be bolted and fixed permanently in place. Or, and honestly, this is a brilliant feature for shipboard maintenance, they can be mounted on a withdrawable truck, kind of like how the main circuit breaker itself is mounted. This is a big deal because it means the technician can physically rack out and pull the VT for inspection or maintenance without having to completely shut down and de-energize the entire board.
But traditional VTs have a bit of a dark side, and it's a massive pain point for marine electrical engineers. It's this phenomenon called ferroresonance. Because a traditional VT relies on a heavy iron magnetic core, it's really susceptible to magnetic resonance during switching transients. Basically, when a breaker opens or closes, the sudden shift in the network can cause the VT's core to resonate, and that produces these wildly inaccurate voltage readings. This erratic behavior often completely mimics a real electrical fault, sending engineers frantically chasing phantom faults while pulling their hair out over problems that don't actually exist in the primary system.
So how do we fix that headache? Enter the modern alternative, the resistive divider. Its absolute secret weapon is a partition ratio of exactly 10,000 to 1. What this means in plain English is that it takes a primary voltage ranging anywhere from 0 all the way up to 24 kilovolts and perfectly, linearly, scales it down to a tiny, completely safe output voltage. It's always directly proportional to the primary busbar with zero magnetic baggage.
When you contrast the two technologies side by side, the fundamental difference really just comes down to the core. The traditional VT relies on a magnetic core, which means it carries the inherent physical risks of saturation and ferroresonance. But the resistive divider, it has absolutely no magnetic core. Because there's literally no iron core to saturate or resonate, the risk of ferroresonance is physically zero. It's a purely linear drop through a resistor stack. No core, no phantom faults.
Okay, let's test this out with a real-world troubleshooting scenario. Imagine you're standing right in front of the switchboard. A breaker operates, and immediately your busbar voltage reading spikes wildly and erratically on the display, and then it kind of slowly settles back down to normal. Based on what we just covered, are you looking at an installation using a traditional VT or a resistive divider? Think about it for a second.
If you guessed a traditional VT, you hit the nail on the head. That specific transient spike and settle pattern happening right after a switching operation, that is the absolute signature of ferroresonance. A resistive divider physically cannot produce this kind of erratic behavior because its linear coreless physics just simply do not allow for magnetic resonance. So, if you see a phantom fault spike like that, you know exactly what hardware is sitting behind the panel.
All right, let's bring this all together. You now have a complete top-down view of your marine switchboard sensor toolkit. You came into this pair of explainers maybe only knowing sensors existed somewhere in the metal cabinet. But now you can name every single option. You know wound core CTs are for standard current. You know toroidal CTs catch earth faults. You know Rogowski coils never saturate during massive current spikes. You know traditional VTs are resin insulated but carry that risk of ferroresonance. And you know resistive dividers offer a perfectly linear 10,000 to 1 ratio with zero resonance risk. You're now fully empowered to diagnose and understand every single one of these on site. But here's a final kind of provocative thought to leave you with. Everything we've covered so far, the CTs, the dividers, the Rogowski coils, they really only inform the system. They're just the eyes and ears, right? They don't actually do anything to stop a catastrophic failure. So, what happens when those sensors actually detect a massive violent short circuit? Well, in our next explainer, we're going to look at the device that violently acts on that information, the medium voltage circuit breaker, and the frankly incredible physics of arc extinction. It's going to be a great one. You won't want to miss it. See you then.